I divide my talk three different parts. The first part is generally introduction of fast mass experiment, and then we have short break for Q&A. Then following the first short break, I want to show the several aspects of proton NMR, where the fast mass is heavily used. Then following the second Q&A session, I will show you the 2D proton-based experiment at fast mass. So let me start from the first topic, the introduction of very fast mass. This picture is taken from Joseph's laboratory and from Warwick University. This picture clearly shows the diversity of mass rotors from the very large unsampled rotor to small rotors. In most cases, we use the sample rotor from 3.2 to about 5 millimeter. So these are kind of general solid state NMR rotors. I think the 90% of solid state NMR is observed with these rotors. But one of the limitations is spinning frequency. In these rotors, spinning frequency is typically limited to 10 kHz to 20 kHz. If we need much faster spinning frequency, we need something more. To this end, many tiny rotor is developed in these 10 to 20 years. Then one of the advantage of such a tiny rotor is, as we discussed, fast mass. We can achieve very fast mass with these tiny rotors. Then there is several side effects. One of the side effects is sample volume. Since sample rotor is very tiny, we don't need huge sample amount. If you have 1 milligram of sample, that is more than enough. This can be disadvantage. Because of sample volume, maybe we lose sensitivity. But this partially alleviates by the high sensitivity per unit volume. This is simply because we have very tiny sample coil, and this gives us very efficient conversion from magnetic field to the electric current. This also provides the very strong RF field strength in these sample and small rotors. I think most of them you already know what is magic angle sample spinning. Magic angle sample spinning is widely used in solid state NMR. If you spin your sample along this axis, that makes the magic angle from the such magnetic field. We can average the anisotropic interaction in the time averaged manner. And then we have high resolution NMR spectrum. We have to spin the sample very fast mass rate. As we discussed, now the spinning frequency reach higher than 150 kHz. This is very rapid in terms of angular frequency. But this is also very fast at the surface, speed at the surface, speed at the surface, I mean the linear velocity. If you look at the speed at the surface, this is close to the speed of the sound. So if you rotate your sample rotor on this road, you can roll around the Earth in 44 hours. So you can imagine, you can see how rapid the spinning rate is. Then, benefit of magic angle sample spinning is resolution. This is an old example taken from textbook. Without spinning, we have very broad line shape for carbon-30 NMR spectrum. But magic angle sample spinning get rid of this broadening, and then we can enjoy high resolution NMR spectrum, similar to the solution NMR. So this is why we need magic angle sample spinning. So as you see, the drastical effect of magic angle sample spinning. One question is magic angle sample spinning magic? You can see this broadening can be removed with magic angle sample spinning. Yes, magic angle sample spinning is quite useful for particular kind of broadening, but in the other broadening, magic angle sample spinning doesn't work. So that depends on the source of the broadening. If you are working on the isolated nuclei, And broadening, if your broadening comes from these interactions, we can remove broadening by magical ensemble spinning. However, the line shape doesn't depend on spinning frequency. So in this case, maybe magical ensemble spinning first mass is not required. Here is one example of this sample. When you set up the solid-state NMR experiment, I think most of you use KBR to adjust magic angle. Here is FID observed with this sample. You see very strange FID. Not only just a simple decay, you see a lot of numerous spikelet. This comes from rotor echoes. The satellite transition in KBR is broadened by the first order quadrupolar broadening. Then this is removed by magic angle sample spinning. But that refocus at every rotor cycle, and that results in this kind of spikelet. Then if you adjust magic angle correctly, you can see a lot of these spikes. So simply we have to maximize these spikes by changing the magic angle. If we apply Fourier transformation, we can obtain spectrum. Then you see the numerous sideband appear together with center band. Then if you look at this spectrum carefully, you don't see any dependence of spinning frequency of this line shape. So line shape doesn't change at spinning frequency. So in this case, maybe first mass is not a good way. But even this sample, first mass, is quite beneficial to improve sensitivity. Here is one example of heavy half-spin, half-nuclei. Most of the heavy spin half-nuclei have very large chemical shift anisotropy. So we can obtain very narrow line shape, but that is consisted of numerous spinning by sideband. Here is one example. This spectrum is observed with 4 mm rotor. Then because of the limited spinning frequency, we see numerous spinning sideband at every rotor period. Then one problem is, as a 4 mm rotor, we have limited RF field strength. So we cannot excite everything at the same time. So we have to correct several different spectrum by changing the offset. And by adding everything, we can obtain this kind of spectrum. So this is a bit time consuming. And since the signal intensity distributed to many spinning sideband, this also reduces the intensity, the sensitivity. In addition to that, it is quite difficult to find where is the isotropic chemical shift. In this case, isotropic chemical shift is here, but we have to change the spinning frequency to find where is the isotropic chemical shift. Or maybe we can simulate it by fitting the line shape. But anyway, this is a bit time consuming. But for this sample, if you spin sample very fast, you see the quite good improvement. We have much less spinning sideband. Then it is very clear to find the isotropic chemical shift. In addition to that, all the signal intensity is folded as a center band, and that improves the sensitivity significantly. So if we look at these two spectrum, these two is observed with almost same experiment time, but we can get the almost same signal to noise ratio. I think this is amazing if we think about the difference of sample volume. So for this sample, first mass is quite beneficial, even though line shape doesn't change at spinning frequency. So this is first mass improved sensitivity. Here is another example for paramagnetic sample. In the paramagnetic sample, we see huge broadening because of the paramagnetic broadening. Then first mass help to improve both sensitivity and resolution. If your sample suffer from paramagnetic broadening, we can try fast mass experiment to get the good spectrum. So, for the other first introduction, yes, we can suppress spinning sideband and we can improve the sensitivity. This is also true for the paramagnetic sample. But the line shape doesn't change depending on the spinning frequency. For if your broadening comes from chemical shift anisotropy and quadrupolar interaction, so then if you need higher resolution, we have to think about something else. So another example is second order quadrupolar broadening and residual dipolar splitting. For this interaction, that come from the multiplication of two second rank tensor that result in 0th second rank and 4th rank tensor. 0th rank tensor doesn't do anything for line broadening. That's fine. And for the second order tensor, we can get rid of by magic rank sample spinning. But for 4th rank tensor, magic rank sample spinning only partially reduce the line width. And we cannot reduce a line width by spinning fast. So for this sample, fast mass is not useful. Here is one example of chloride NMR spectrum. If you observe chloride NMR spectrum at 600 MHz magnet, you see huge broadening coming from second order quadrupolar broadening. Since this is described by the 4th rank tensor, we still have residual broadening. Then this broadening doesn't depend on spinning frequency, so fast mass doesn't help for this kind of broadening. The easiest way is just increase the magnetic field, and we have narrower line shape. As a high magnetic field, sometimes we see large spinning sideband coming from chemical shift anisotropy. Chemical shift anisotropy is proportional to the magnetic field. So as a high magnetic field, this may contribute the signal intensity to the spinning sideband. In that case, fast mass may help. But in most cases, the line shape doesn't change at fast mass. In order to remove this line shape, you can use MQ mass experiment or ST mass experiment or some special equipment to get rid of second order quadrupolar broadening. Residual dipolar splitting is something similar. This is observed in spin half nuclei next to the quadrupolar nuclei. The famous example is carbon-13 NMR spectrum in amino acid or protein NMR spectrum. Both of them suffer from residual dipolar splitting. Then fast mass doesn't help to remove this broadening. Another consideration is sample quality or heterogeneity. This is carbon-13 NMR spectrum of protein. This is the crystalline sample. In these cases, we have very narrow line shape because of the uniform conformation. But your sample is prepared by lyophilized sample. You see huge broadening due to the structural distribution. In this case, fast mass doesn't help. So my message is we have to understand where broadening comes from. So depending on the broadening, we can use fast mass or another method. So this is the first part of my talk. Then now we have time for short Q&A.
So if you have any questions, please post your questions in the Q&A window in the Zoom webinar. Yusuke, if you have this window open, you should be able to look at the questions. Yeah. So I can read the first question from John. Can you compare the advantages of faster MAS versus CRAMPS?
Yes, I have a question in the following slide. Maybe we can quickly go there. Yes, this is a comparison between the fast mass experiment and the PMLG experiment. My answer is if we use the CRAMPS experiment, we can obtain the similar or even better resolution compared to the fast mass experiment. But still, fast mass has several advantages. One thing is, in case of fast mass, we don't need any special observation. So we have very high sensitivity observation. Then in case of the PMLG, we need kind of Windows equation. Then that reduces the sensitivity. And important point is, I think, the quantitative information. I mean, we can count number of protons by the single pulse experiment. In this case, this is quite useful for practical application. This is useful for the spectral assignment, and this is sometimes useful to understand the ratio of two different conformations. So this is only available for fast mass experiment. And another advantage is easy setup. In the fast mass experiment, all we need is just spin fast and then pulse it, and we can get this kind of spectrum. Yes, my answer is resolution. Yes, we can get the good resolution with CRAMPS experiment, but still the fast mass is quite beneficial in many different times.
Right, thank you. So the next question is from Eddie Saliba. Were the spectra that were pieced together excited adiabatically?
Yes, yes, right. Let me check it. If I remember correctly, that is adiabatically excited, but I need to check it, double check it. But that is already published in the 3 years ago.
Okay, so the next question is from Professor Ramamurthy. Is there any way to overcome the anisotropic bulk magnetic susceptibility line broadening under fast MAS?
If that comes from just the bulk magnetic susceptibility, in this case, that is the second order broadening. Then a second order that is described by the second order tensor, then we can get rid of this broadening by magical sample spinning. So, but if your sample has anisotropic bulk magnetic susceptibility, in this case, the resulting line shape is determined by the shape factor that is described by the second order tensor and the magnetic susceptibility tensor. This is also second order tensor. That results in fourth order tensor, fourth rank tensor. With that, we cannot get rid of by magical sample spinning. Then, if in principle, we can remove this broadening by the door or that kind of experiment, but of course, this is technically very demanding. So at this moment, this is, I think, a very big issue, especially for the pharmaceutical application. If your sample has aromatic ring, we have large anisotropy in magnetic susceptibility tensor, and that typically result in the broadening of 1 pp or something like that. This is huge for proton NMR experiment. I think this is we have to solve in these maybe 5 years or 3 years.
So the next question is from anonymous attendee. Mathematically, how does the loss of signal due to lower sample volume compete with the improvement due to the smaller coil?
Yes. So then that quite depends on the system, and this also involved in the my talk. If you look at the yeah, this is also Amrit, you are involved in this research. So this is the comparison. Or okay, maybe we can go from this slide. This is the comparison of proton detected nitrogen 15 experiment and nitrogen directly observed spectrum on natural abundance sample. As you can see, the proton detection improved the sensitivity a lot. But then it seems this is quite good. But actually, this is not a fair comparison because for the direct observation, we can use much larger sample rotor, and then we can get much higher sensitivity. I think the fair comparison is something like that. we can use large rotor for direct detection, and we can use small rotor for indirect detection. Then for low gamma nuclei, we have quite good sensitivity improvement. This is true. And in the practical application, many of the experiments, we need carbon-13 NMR spectrum and nitrogen-15 experiment. In these cases, the actually proton detection do not provide higher sensitivity than 3.2. In this case, we should use large sample rotor. So sample volume is important for these experiments. But in case of nitrogen-15, the sensitivity of direct detection with standard rotor is more or less the same as proton detected experiment with 1 mm rotor. So in this case, sensitivity loss is overcome by proton detection experiment. So that depends on the system and that depends on nuclei.
Okay, so the next question is from Dahiana. Can you comment on the effect of hard pulses and soft pulses to excite different spins and the use of it?
Hard pulse, soft pulse to excite different spins. What different spin means?
I think they mean different kinds of nuclei.
Okay. I don't get the question exactly, but if you generally, if you want to excite, okay, in case of the spin half nuclei, if we want to excite a broad range of spectrum, we should use hard pulse, and if we use soft pulse, we can limit the excitation range, and we can use these pulse as a selective pulse. In case of the spin, not spin half, but quadrupolar nuclei, we have to be careful about the interference to spinning frequency. Typically, we use the central transition selective pulse. Yes, I hope that is the answer. But if that is not a good answer, please ask again.
Yeah. Dahiana, please let us know or raise your hand during the next Q&A session, and then we can maybe allow you to talk and ask the question yourself. So maybe we should move on with the talk and answer and revisit the Q&A session again.
Okay.
Yeah.
So yes, we are here. So next, I want to talk about the proton NMR. We use fast mass experiment to observe proton NMR spectrum. In case of proton NMR, proton is connected to each other, and that forms kind of network. In this case, the proton-proton dipolar interaction do not commute each other during the spinning, during sample spinning. Then this introduces the homogeneous broadening. The effect of dipolar coupling is removed as the first order under the magic angle sample spinning. Then, however, because of the this homogeneous nature, line shape is broadened by the higher order terms. Then size of the higher order term scales as inverse of mass rate. That means if we use spin fast, we can reduce line width. So that's why we need very fast mass for network of homonuclear dipolar coupling. Here we show the effect of the network. This is fully protonated peptide, NMR spectrum. You see the huge broadening due to the homogeneous broadening. Then, if we observe the NMR spectrum with partial deuteration, you see significant improvement of resolution. But for this experiment, we need to modify the sample. We can obtain the same effect by fast mass experiment. If we observe NMR spectrum at several different spinning frequencies, you see significant improvement in terms of resolution and sensitivity. So that's why we need fast mass experiment. Actually, effect of magic angle sample spinning is not linear. The 2 years ago, Joseph also showed the relationship between T2 prime, that is spin echo coherence time, and the spinning frequency. Actually, this is not linear, so this is quadratic relationship. There is still many discussion. Where is the source of these factors? But anyway, bottom line is faster the better. We can obtain much narrower line width and longer coherence lifetime. Then this is, we already discussed, this is comparison between the single pulse experiment and Windows PMLG experiment. Then we can obtain high resolution, high sensitivity spectrum at fast mass, and we can count the number of spins by the signal intensity, and the setup is easy. Actually, Windows PMLG suffer from many experiment setup. The detailed discussion is published in the Matthias Ernst. I think that is the early of, I think this year. But there is many discussion. The bottom line is the, for example, inhomogeneity of RF field also provide the broadening. It can be a source of the broadening in PMLG experiment. So another benefit of fast mass experiment is there is a lot of low power sequence, and we can reduce the sample heating by RF irradiation. In many of the organic sample, we have to apply intense proton decoupling to kill the dipole interaction from proton. This is carbon-13 NMR spectrum. Then typically we need high power decoupling for proton decoupling. But now we spin the sample as a very fast mass rate. Then most of the dipolar coupling is already averaged out. Then what we have to remove is residual dipolar broadening. Then we don't need strong RF field. We can use weak RF irradiation to remove this residual broadening. Then typically we need maybe 5 kHz or 10 kHz of irradiation. Then if you look at the RF input, you see the significant decrease. For example, if your probe achieves 300 kHz irradiation with 50 watts input, 10 kHz is obtained with only 55 milliwatts. This is almost nothing. Then we can apply decoupling as long as you want, and of course we can avoid sample heating. This is decoupling. Another aspect is cross-polarization. In order to transfer magnetization from proton to the other nuclei, we can use cross-polarization if both is unspin half nuclei. Then in this experiment, we have to carefully adjust the RF field strength for proton and carbon-13. The traditional CP condition is here. If we use the same RF field strength for proton and carbon-13, we can transfer magnetization between these two. Then this condition split into 4 at magic angle sample spinning. Here, 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 here. So in this condition, the difference of RF field strength is 2 omega R or 1 omega R. But in these 4 conditions, we use flip-flop term. So the residual resulting signal intensity has the same sign. For the standard experiment, we use this kind of regime. But this can be problematic for fast mass experiment because this is 2 times of spinning frequency. So if you spin the sample at 100 kHz, that means we have to apply RF fields stronger than 200 kHz. This can be too much for your sample or maybe your probes. But fortunately, we have low power regime for cross polarization. That is here and there. That is double quantum CP. In this condition, we set the RF field summation of RF field strength of proton and carbon-13 is equal to spinning frequency or 2 times of spinning frequency. In this case, we can reduce the RF field strength dramatically compared to these conditions. But in this condition, we use flip-flip term for magnetized transfer. That means we have opposite sign of signal intensity compared to zero quantum cross polarization. So if you phase it with positive signal, you obtain negative signal for these conditions. Then this is a big issue for this crossing point, because here the zero quantum CP give us positive signal, and double quantum CP give us negative signal, and then these two cancel each other, and then finally we observe nothing. So we have to avoid these crossing point. So in that sense, at the double quantum condition, we have to carefully choose the experiment condition. In case of the proton and carbon-13, we typically use this regime. Here, for example, if you spin sample at 70 kHz, this is 70 kHz, this is 35 kHz. In order to cover the carbon-13 chemical shift range, we prefer to apply stronger RF field to carbon-13. Then we can reduce the RF field strength to proton. Then we typically use 15 to 20 kHz for proton irradiation and 50 kHz to 55 kHz for carbon-13. Then we can choose this condition. But that quite depends on nuclei. If your X nuclei do not have so much wide chemical shift range, you can use this condition. This is especially true for low gamma nuclei. In case of low gamma nuclei, we cannot achieve high field irradiation along this axis. Then we can use these conditions instead of here. So that depends on the nuclei, and that depends on the chemical shift range of your sample. But anyway, as you can see, if we use this condition, we can reduce the RF field strength compared to the zero quantum cross polarization, and we can enjoy low power cross polarization. So that is the other advantage of fast mass experiment. Then there is a lot of many other experiments. As we discussed, fast mass remove the heteronuclear or remove the anisotropic interaction. But we can reintroduce these interactions by irradiating rotor synchronous irradiation. We already see one example. In the cross polarization, we utilize heteronuclear dipole interaction. Heteronuclear dipole interaction is already removed by magic angle sample spinning. But if we carefully adjust the RF field strength, we can reintroduce the proton carbon-13 heteronuclear dipole interaction. So this is one way to recouple heteronuclear dipole interaction. And this experiment can be used for distance measurement between the proton and X nuclei. And then similarly, we can recouple many other anisotropic interactions. One example is proton chemical shift anisotropy. This is quite good source of information, especially for hydrogen bonding. And recently, one group from the Lyon in China published a very nice review article on these aspects. And first target of fast mass experiment is homonuclear dipole interaction. We want to get rid of the broadening from the homonuclear dipole interaction. However, of course, we can recouple it. This is one example from our group together with Vipin. We can measure the proton-proton distances in the quantitative manner by selectively recouple the homonuclear dipole interaction. But anyway, my message is we can design many different recoupling sequences, although most of the interaction is already removed by fast mass experiment. Then we can, especially we can selectively decouple interaction to get the local information. So then this is the first advantage of fast mass experiment for proton experiment. We can obtain high resolution spectrum by fast mass, and we can use low power sequences. And we can also design the recoupling sequences. So now we have time for second break for Q&A.
Okay, please type in your questions into the Q&A window. So we have a couple of questions there. So the first question is, does chlorine actually benefit from MAS? I was under the impression that chlorine spectra are only useful if static ultra-wide line experiments are performed. Professor Bryce has already answered with this comment that it depends on the size of the quadrupolar interaction.
Chloride experiment is, okay, first mass is not suitable direct observation of chloride experiment because spinning frequency doesn't help to reduce the line width. But if we observe indirectly through proton, we need fast mass. Then we can observe chloride not only the center band of the chloride, central transition line of chloride, but also the satellite transition of chloride. Then, for example, if you look at the distances between the central transition and satellite transition, we can estimate the size of the quadrupolar coupling quite easily. So in this sense, I think that of course depends on sample, but if your sample has proton close to the chloride, fast mass is still a good option for chloride measurement. Of course, we can try worst excitation or something else. That depends on sample. But the fast mass is still one good option of these experiments.
All right. So the next question is from Ulrich. How difficult is it to spin paramagnetic samples, and what is the related sample heating?
Okay, for the paramagnetic sample, if that is just a paramagnetic, nothing difficult. Just put the sample and spin it in the magnetic field. Then for the sample heating in case of paramagnetic sample, that solely comes from friction to the from the air and the surface of sample rotor. Then typically this friction is the power of 2.5 of spinning frequency. So for example, if your spinning frequency is maximum spinning frequency is 100 kilohertz, and you can get I don't know, maybe 30 degrees Celsius from the room temperature. You simply reduce the spinning frequency slightly, maybe 80 kilohertz. The sample temperature is almost close to the room temperature, and we can avoid the sample heating by this manner. But if your sample is not only the paramagnetic, but also maybe just magnetic, for example, some magnetic, or if that is conductive material, the spinning can be very difficult. In this case, we dilute the sample with inert sample, or just restrict the sample volume by putting spacer. So in this case, we have to be careful about that. And in addition to that, we also suffer from heating by the eddy current. Then we have to be very careful about it. For example, if we put the solder on the sample rotor, we can easily melt it. So sample temperature can easily heat it up higher than 200 degrees Celsius. So we have to be careful about that.
So the next question is from Anonymous. What do you think about the prospect of ultra-fast spinning spheres? Can it be faster than a cylindrical rotor?
Yes, this is very interesting article. One thing is faster than thing. Of course, I personally don't have any experience of spherical mass rotors, but I think the fast spinning frequency, in terms of spinning frequency, this still cylindrical rotor is beneficial because the spinning frequency is limited by the materials. We can, for example, 1 millimeter rotor can spin up to 80 kilohertz. This limitation comes from strength of sample rotor. If we spin faster than 80 kilohertz, that simply breaks. Then in terms of that, I think the cylindrical design is the best option for fast mass experiment. But in the spherical rotor, as the author mentioned about in the first article, there is a lot of different advantages. For example, there is open space for DNP experiment. So I think we have to choose the appropriate design depending on applications.
Okay, so the next question is, sorry. So I think Dahiana has gotten back on her question about the soft and hard pulses. So for quadrupolar nuclei, for instance, MQMAS, the setting of the experiment requires the optimization of hard and soft pulses. So I would like to understand what would the effect of selectivity of excitation and the need of it.
Okay. For my personal experience is if we working on the MQMAS experiment, I think we should use a slightly larger rotor, like a 2 millimeter or 3.2 millimeter rotor, because yes, we can achieve a very strong RF field if we use very tiny rotors, but that also sacrifices the sensitivity. And in MQMAS experiment, we directly observe signal. So the sample volume is very important. So in case of MQMAS, I think 2 millimeter or 3.2 can be the good option. This is the compromise between RF field strength and the sample volume.
All right, so if that is the case, maybe we can move on with the talk since we have no more questions at the moment.
Okay, so the next topic is, the final topic is 2D experiment, proton detection experiment. Obviously, the easiest 2D experiment is proton-proton correlation experiment. This is just a noisy experiment. We have single quantum evolution in this dimension, and we have mixing time, and finally we observe NMR signal. Then in this experiment, we can obtain the proximity between the spin A and spin B from this cross peak. If we have cross peak, we can say these two are close to each other. The benefit of single quantum experiment is it's quite easy to perform. And we can put very long mixing time because magnetization is stored along the axis. Then we can obtain the long range correlation. Especially in this experiment, we have relays transfer as well. So this is a benefit of single quantum correlation experiment. But one of the problem is we always have signal on the diagonal line with a slope of 1. So this do not mean spin A is correlated to spin A. So this is the one of the and if your cross peak appear close to the diagonal line, maybe this is obscured by the presence of intense diagonal peaks. This problem can be solved by double quantum single quantum correlation experiment. This is very similar to single quantum experiment, but simply replace the first dimension to double quantum. Then we in this period, the magnetization evolved the summation of chemical shift of spin A and spin B, and that will convert to the single quantum frequency of A and B. Then in this experiment, all the peaks come from double quantum coherence. That means all the peaks come from pair of spin interactions. Then if you plot the diagonal line with a slope of B, a slope of 2, if you have cross peak, diagonal peak, B and B, that means B is sitting next to another B. So we have B-B correlation here. Then if you don't have correlation A and A, that means A is isolated from the other A. So from the presence and absence of diagonal line, we can discuss the connectivity between the same kind of nuclei. And the correlation between A and B appear as symmetrically from this diagonal line. And from these two peaks, we can say we have correlation between A and B. So this is double quantum, single quantum correlation experiment. The difference from single quantum experiment is one is information on the diagonal line, as we discussed. Another feature is because of the dipolar truncation, we can observe only short range correlation, typically shorter than 4 angstrom. So this is a big difficulty compared to single quantum experiment. But there is some limitation from the experiment setup. In most of the double quantum experiment, we have to set up the experiment F2 dimension synchronized to sample spinning. For example, if you spin the sample at 100 kHz, the indirect dimension must be 100 kHz or maybe 50 kHz, 25 kHz, 33.3 kHz, or something like that. This is because this is the indirect dimension of double quantum, single quantum experiment, and this is double quantum dimension. The peak appear not at the center, but at the spinning sideband. This depends on the sequence you used for excitation and reconversion. In case of the non-gamma encoded sequences, these peaks appear the positive and negative spinning sideband. In case of the gamma encoded sequence, the peak only appears at one side of the spinning sideband. But anyway, this is the center of the peaks. Center of the peaks. In order to obtain the standard this kind of spectrum, we have to synchronize the sample spinning to. We have to synchronize the indirect dimension to the sample spinning. Of course, in case of gamma encoded sequence, this is just a shift. This is not a big issue. But in case of the non-gamma encoded sequences, these two signals appear in the same area. So we have to avoid the non-synchronous observation. So this is the proton double quantum single quantum correlation spectrum. Then, of course, this is quite useful, not only the proton, but also the Florin experiment. In case of Florin experiment, the spectral range of indirect dimension is quite important. So this rotor synchronization or maybe gamma encoded sequence is quite useful. We have to think about these aspects. So here is another example of proton detected experiment, heteronuclear experiment. Simple experiment, just proton to nitrogen 15 cross polarization. And typically we directly observe carbon NMR spectrum here. But in case of the indirect detection, we convert this magnetization back to proton and we observe proton NMR spectrum. So from that, we can obtain the 2D heteronuclear correlation experiment. The obvious benefit is sensitivity enhancement. As you know, in solution NMR, HMQC and HSQC is widely used for sensitivity enhancement method. So this is the same approach for solid state NMR. Then as we show, you can see significant improvement of the sensitivity by proton detection. But we also need to think about another factor, sample volume. For direct detection, we don't need fast mass, small rotor. We can use standard rotor, and we can put a lot of sample in it, and we can obtain higher sensitivity than 1.2 or 1.3 millimeter, 1 millimeter rotors. But even though the proton detection gives us higher sensitivity than direct detection. So for these low gamma nuclei, we should use proton detection if your nuclei has proton neighbor. Then this is another comparison for carbon-13. Carbon-13 has higher gamma ratio than the tungsten or silver. Then we can obtain reasonable signal intensity for standard mass rotors. And sensitivity compared to the proton detected proton is 5 times more in case of here. That means if you need just a CP mass 1D spectrum, I recommend standard rotor. This is much better than the proton detected one. But if you need this 2D experiment, we see almost same or even better sensitivity in proton detection experiment. Then in this case, I can recommend proton detected experiment at first mass. One problem would be the absence of quaternary carbon. In this case, we should use the 3.2. But in most cases, I think the proton detection is better for proton X 2D experiment. And as we discussed, the sensitivity enhancement is more dramatic in low gamma nuclei. In case of nitrogen 15, we have sensitivity of like this with standard rotor. Even 2D experiment, we have almost same sensitivity. So that means if we use proton detection with smaller rotor, we have almost same sensitivity, and we have another proton dimension to observe 2D spectrum. So in this nuclei, I recommend proton detection, even though the sample volume is limited. So the proton X nuclei is quite useful sensitivity enhanced method, especially for low gamma nuclei. Then first mass also allow us to observe something else, some strange nuclei. One of the my favorite is nitrogen 14. We can indirectly observe nitrogen 14 by another spin half nuclei that is parallelly developed by the Xeon Gang and Geoffrey Bodenhausen in 2006. Then if we measure it by proton at faster mass, maybe 70 kHz, 80 kHz, 100 kHz, we can quickly observe nitrogen 14. If you think about the abundance, this is quite natural. Both of nuclei is almost 99% of abundance. Then we can easily find this pair, and then we can obtain very high sensitivity spectrum. Actually, we spend only 2 minutes to get to this spectrum. It's quite easy spectrum experiment. This is supported by the sensitivity enhancement by fast mass. Then there is several different way of magnetization transfer. At this moment, okay, as the beginning, DHMQC is used, or just HMQC is used, but some trapdoor based experiment or WCP experiment is also proposed. And quite recently, the one comprehensive research is published from the NHMFL. Based on that, this THMQC looks the best one. Then I'm also independently verify these effects. At this moment, I'm in the middle of these two, but I think, okay, my message is this is still developing field. Then here is another example. Nitrogen 14 is exciting nuclei, but there is a lot, something else. Here is one example for distance measurement between the proton and kappa. Kappa is also attractive nuclei for material sciences. Then we try to measure the distance between these two. Then we have very interesting material. This is one of the MOF sample, but we can also design or develop the glassy MOF. In case of glass, there is no way to understand the structure except for solid state NMR. And from solid state NMR, this clearly shows we see the similar distances between the methyl proton to kappa, but after vitrification, we see the longer distances as aromatic proton and kappa. So this kind of information is only available NMR experiment, only available from solid state NMR, and especially at fast mass. For this application, I think the fast mass is quite useful. And there is a lot of unknowns. This is one example published from BPIN this year. If we simply measure just a proton single quantum correlation spectrum, we only expect the positive signal if we have only dipolar transfer, but we observe some negative signal it looks like the NOE in small molecule of solution NMR, but this is something different. This is clearly explained by the flip-flop force spin terms. So this term, we never think about it, but this has significant effect on this correlation experiment. Proton-proton experiment is very fundamental, simple, basic experiment, but still there is a lot of unknowns. So my message is there is a lot of field to work on. So then first mass experiment, if we use proton detection, we can observe many different strain nuclei by HMQC or something else. So then here is, this is kind of advertisement. This is the several book chapter we contributed and one review article on fast mass experiment. What I talk today is everything is written in this article. And here I didn't mention anything about biomolecule, but there is a lot of application of fast mass experiment on biomolecule. So here is the several reviews of biomolecule experiment. Okay, thank you.
Yeah, thank you so much, Dr. Nishiyama. That was a excellent talk, and I personally really enjoyed just listening to you talk about this. So maybe before we continue to take some questions, I would just like to say that our next week's speaker is Dr. John Blanchard, and he will be talking about 0 to ultra low field NMR. And maybe if you and Vipin are available, we can continue to take some questions that we have. Sure. Since we are just running short on time. All right. So if that is the case, so maybe the first question is from Henry Colo. So low power decoupling allows lower sample heating, but fast MAS increases sample heating. Do you have a comparison of the competition between the two heat sources? So Vipin had added some of his thoughts on that. Yeah.
Yes, we have two different sources of heating. One is from RF field irradiation. The other is from sample spinning. Then there is huge, big difference between these two. In case of the sample spinning heating from the friction, we can reduce it because this is continuous heating, and we can simply apply continuous cooling, and we can remove this effect. But in case of RF heating, we have very short irradiation, maybe 1 millisecond, 10 milliseconds, maybe 50 milliseconds. So sample temperature quickly grow up at the irradiation, and that drop rapidly. This kind of heating is very difficult to handle by cooling air. Then because of that, RF heating is much more harmful for NMR experiment. Then we have to use the low power decoupling to avoid that. And for the friction heating, yes, it's there, but we can easily handle it by applying the cooling air.
So the next question is from an anonymous attendee. What about infinite MAS? Won't this lead to suppression of these higher order terms?
Yes, higher order terms, yes, and that is higher order terms will be removed by the infinite mass experiment, mass spinning frequency. But as we discussed, there is a lot of many different sources of broadening. For example, in the static, for the small molecule, the large amount of broadening come from anisotropic bulk magnetic susceptibility, which we cannot remove magic angle sample spinning. And even if we have small heterogeneity, that is the source of the broadening. So we can enhance, we can prolong the T2 relaxation at infinite max frequency, but we cannot get rid of all the broadening. So that depends on the what we need. If we need very long coherence lifetime, yes, infinite mass is helpful. But if we need high resolution, we should think about something else.
Right. So the next question is from Professor Bodenhausen. Can you elaborate why some 14N indirect detection methods are found to be better than others?
Okay. In case of the direct detection, it's quite difficult to observe because of the presence of the large quadrupolar coupling. So for example, if we simply just observe nitrogen 14 for single pulse, we don't see anything even for glycine. Glycine has very short, small quadrupolar coupling. It's only just 1 megahertz, but this is too big. Then in order to observe it, we need worse type experiment. But still, experiment setup is big challenging. And if your dipolar coupling and quadrupolar coupling is larger than 4 megahertz, even worse, it's quite difficult to set up the experiment. But for proton indirect detection, it's much easy to set up. And because of that, I think the proton detection is beneficial over the other method. But one of the difficulty problem is if we only observe nitrogen 14, we don't have any idea the size of the quadrupolar coupling. We have to compare two spectrum at different magnetic field. And from that, we can understand the size of the quadrupolar coupling. And another way is maybe we can compare the NMR spectrum for nitrogen 15 and nitrogen 14. But anyway, we need two independent experiments to obtain the size of the quadrupolar coupling. This is one of the limitations. But still, I believe the proton detection is better than the direct detection.
All right. So just going back to that question on spherical rotors and the comparison with cylindrical rotors, I think Vipin had some thoughts to share on that. Vipin, do you want to unmute and share your thoughts? Yeah.
Sure. So Yusuke mentioned one factor, that's the strength of the material, but we should also consider another factor that is limiting, and it's the speed of sound. And we know when we get to the speed of sound, you know, we get into this Mach regimes of supersonic booms, etc. that happens. And already when you get to 80% of the speed of sound, then you start getting these shock waves, and these are unpredictable shock waves. So if you typically convert your angular frequencies into linear velocities, what you find is that most of these fast spinning rotors, they are about 250 to 260. I think the one from Argo is about 267 meters per second. And of course, JEOL has one which they claim 0.75 spins to 120 up to 120 kilohertz. But that's also, you're getting into 280. So you're getting about 80% of the speed of sound. And that's where the uncertainty comes. And now if you start putting in cooling gas, pressure, humidity comes in, and then your sound changes. So the point is that if you're getting up to these 80% velocity of sound, relative velocity of sound, then I think crashes are imminent. And that's why we see that that becomes the limiting factor. So if you start spinning in helium, of course, one can spin much, much faster there, because there also the sound travels faster, and that's why in helium you actually can spin much faster. Now, coming to spherical rotors, I mean, I think most of us have not handled them. We have to see how far they can go, because also the spinning that is being done for spherical rotors is in helium gas versus what we all do, pretty much spin in nitrogen or air. So that's another factor that one has to consider on spinning fast.
Yeah, thank you, Vipin. I think your question also answers one of the other questions that another anonymous attendee had about using helium to spin faster at low temperature. So maybe just moving on, a question from Dahiana. What would be an optimal experiment to measure fluorine, which has huge homonuclear dipole-dipole interaction?
Optimum experiment, optimum for high resolution. Typically, fluorine experiment is easier than proton experiment to remove the homonuclear dipolar coupling. This is because we have large separation of chemical shift, and that truncate the homonuclear dipolar interaction. Then typically we can use much slower spinning frequency than protons. So I think for the nitrogen, no, it's not nitrogen, fluorine 19, it's much easier than proton. actually, we don't see so much resolution improvement at a very fast mass rate. But another problem is, again, wide spectral range. We have to excite everything. Yes, if we just measure single pulse experiment, we can excite everything. But if we want to decouple interaction between these nuclei, this is something sometimes challenging. Some of the decoupling sequence has limited bandwidth, and we can only excite part of that. Then we have to carefully choose the sequence to get the correlations.
Okay, so the next question from Raj, I think you touched upon some of these points. What are some examples of situations where it would be more advantageous or necessary to use slower MAS spinning frequencies?
Okay, the slow spinning frequencies.
Amorphous materials, when you have heterogeneity, broadening due to heterogeneity, for example, in your polymers, etc., there you would not really benefit, spinning faster because it's the other side of broadening.
That's right. For this sample, fast mass is not beneficial, not benefit for the experiment, but only disadvantage is sample volume. So I think we have some weeks. Let me think. Yeah, if the broadening is dominated by the heterogeneous broadening, definitely slow mass is better because of the sample volume. But
Charlie, of course, says that if you want to determine tensors, for example, where you use your spinning sidebands,
yes,
that's also another application. Of course, you can do sort of recoupling and generate the sidebands, but if you have a limited number of sides, then one can do that very easily.
And one more example is, as quickly mentioned in the paramagnetic sample, in case of paramagnetic sample, broadening may come from temperature gradient across the sample. In this case, we intentionally reduce the spinning frequency to get the homogeneous temperature across the sample. For this case, the slower mass is beneficial compared to the fast mass experiment.
We have a follow-up question to the same discussion from Aaron. In a disordered material, would the broadening of the 13C signals not make proton detection a more appealing option?
Broadening for, yes.
I think this is with regard to the point that Vipin mentioned, where you have slow MAS may be advantageous for inhomogeneously broadened amorphous materials.
If we have inhomogeneous broadening in the carbon-13 dimension, proton detection gives us much higher sensitivity than the direct detection. This depends on the lifetime of FID. Then, if for example, if we measure core sample, in core has very broad and big broadening from the heterogeneity. Then, if we directly observe it, FID dump very rapidly. Then we have very low sensitivity. Then in this case, if we use indirect detection, we don't need so much T1 point because FID survive only very short time. Then we can accumulate a lot for each point, and then we can gain significant sensitivity enhancement in this kind of sample. So if we have significant heterogeneous broadening of carbon-13, yes, in that case, proton detection is also beneficial. Yeah, there is a lot of factors. I don't have clear answer to that.
But you see, the heterogeneity goes hand in hand. It's the material, and so if you see it on carbon, you will see it on protons. The only question is how heterogeneous is it, and what other interactions are playing a role. If the proton-proton couplings are also playing a role, then chances are you would not actually be able to record the spectra. So if it's only heterogeneity and there are no other couplings, strong couplings, I think one can get away with it. But if there are other strong couplings combined with the heterogeneity, then I am doubtful that whether proton detection would actually be beneficial.
All right. So the next question is from an anonymous attendee. Could you comment on the practical aspects of sample packing reusability of rotors for 0.7 millimeter rotors specifically?
Okay, for the 0.75, actually it's much tough compared to the 1 millimeter rotor. And typically we damage the cap when we replace the cap. Then, but fortunately, 0.75 is, okay, my comparison is between the 1 millimeter and 0.75. Or in case of 1 millimeter, we can repeatedly use the cap and the sample rotor without any problem. We don't see any damage for the cap insertion. In 0.75, we always see some damage on the cap. But fortunately, spinning is much less affected by the condition of cap. Even severely damaged cap, we can easily spin up to 90 kilohertz. Then for that, in our laboratory, we use cap maybe 10 times or 20 times without any problems. In terms of the sample rotor, we never saw any crash.
Okay, all right. So the next question is from another anonymous attendee. How many protons were used to numerically simulate the PDSD simulations? And in general, minimum, how many of them would be required to mimic the experimental results?
I think we need 100 of the proton. There is one publication from, I think that was Lyndon Emsley laboratory. Then they use the, okay, if we have 100 proton, it is too big to calculate whole matrix. And then instead of calculating whole matrix, we limit the part of the quantum number. Then from that, they can calculate the spin diffusion. Then to reproduce the spin diffusion, I think we need 100 of the proton spins.
All right. So the next question is, would you say ultra-fast MAS could be beneficial for half-integer quadrupolar nuclei as well?
Yes. The one thing is, if you are on quadrupolar coupling very large, we still see huge second-order broadening. Then in this case, we can use proton detection to observe full line shape. And in addition that, even if we have much narrower, we can observe central transition line and satellite transition line to obtain the quadrupolar coupling. I think the even for the spin half, even for the half integer quadrupolar nuclei, proton detection is quite beneficial. And in addition that, not only the direct observation of quadrupolar nuclei, but we can use quadrupolar nuclei to filter NMR spectrum. If we observe proton NMR spectrum, there is a lot of proton. Then by filtering, we can choose one of the proton which is close to the quadrupolar nuclei. This is practically also very useful.
Okay, maybe the last question is from another anonymous attendee. How does proton resolution scale with MAS rate? Do you see a future for higher and higher fields and faster MAS? Or is there room for low field NMR under static? Yeah, that's interesting.
Okay, for the relationship to the spinning frequency, as I mentioned here, not here. Yes, this is not just a linear relationship, but there is a report of the quadratic relationship. So if we think about T2 relaxation time, yes, we do see the improvement at faster and faster mass spinning frequency, but that is finally limited by the inhomogeneous broadening. So that depends on what we need for fast mass experiment. And low field NMR under static, I don't see any resolution at the low field. So if you are interested in the dynamics, in this case, low field NMR is quite beneficial. But for the structural solution, I think we need fast mass or and high field magnetic field to get the higher resolution.
All right, I think maybe with that, we can wind up since we have answered all the questions. Thank you so much, Yusuke, and for your amazing talk today. I think just based on the number of questions and the nice discussion we had, I think a lot of people got benefited. Also, special thanks to Vipin also for joining and just sort of promoting discussion and answering many of the questions.